Thank you for your introduction. So my name is Bruno Coitin. I'm with the IP Networking Lab in University of Louvain in Belgium. And I will present some work we have done with a tool called C BGP. And we applied it to model some aspects of the routing in an ISP. And this is a joint work with Sébastien Tandel, Steve Ulick, and Olivier Bonaventure. So short agenda, first motivate the work, then give a brief overview of the simulator's feature, and show how we apply it on GÉANT, which is the European Research and Education Network. So why would you want to model your network with another tool than current capacity planning tool? Well, it's a lot about the inter-domain traffic and BGP. So it's difficult to predict the impact of a link failure or change in your routing policies, or the addition or removal of a peering link on your inter-domain traffic. Another question is, how can I adjust all the parameters of my network, so BGP policies and so on, in order to reduce my cost, in order to increase my performance, or in order to increase the reliability of my network? So these are the questions we are trying to answer. So in my understanding, this is the view that traditional capacity planning tools have of an ISP network. So it's pretty like an isolated island, not really taking into account what happens outside of your network. But the reality is much more complex. So you have transit traffic, multiple egresses, maybe a complex IBGP structure in your network, including route reflectors, even multiple levels of route reflectors. There are a lot of destinations, so around 215,000 different prefixes in BGP routing tables. And you also have the interaction between an IGP protocol, ISIS, or OSPF, and BGP. So understanding what is going on in an ISP network seems to be pretty hard, and certainly too much for a human brain. So we have developed a tool called C BGP that is able to compute the routes that BGP would have selected in a network based on the knowledge of the topology and the router configurations. C BGP supports most of the BGP decision process, so local pref, AS path length, MED, and other things. It can be configured with different routing policies, so tagging routes with communities, prepending AS paths, etc. It is able to read BGP routes that you would have collected on your border routers, and you can inject them into the model. And it's free. It's an open source tool written in C. And we have currently applied it on 3 different networks, Abilene and GÉANT, and also a French Tier 1 network. So our basic methodology is as follows. So first we have to capture some data into the network to build a view of the topology. We also have to collect information on the BGP sessions, the route maps, etc. And with that, we build the C BGP model. With one view of the model, we can compute what we call the routing state. That is all the routes towards all the prefixes in each router in the model. Then we can play with the model We can change the state of a link in the topology, change IGP weights. We can change route filters, add or remove routes, and see what other routing states we can obtain after the changes. And then we can compare all these routing states in order to figure what's going on. In addition, we are also able to weight these routes with traffic collected with NetFlow, for instance. This is just a sample of the output you could get from C BGP. So it's based on a model of the Abilene network. And the command shown here just display the different steps of the decision process on a single router towards a single destination prefix. So let's go to the case study. So Géant is a network with POPs in all the European capitals. So there are around, I think, 23 nodes. Got more information here. 38 call links and 53 peering links. And among these peering links, 6 are with upstream providers. So we have obtained the Géant topology based on an ISI trace. We have obtained BGP routing data from a Zebra collector connected with iBGP sessions to all the routers in Géant. So we collected all the current best eBGP routes. And in addition, we also get NetFlow data. So the first scenario I'm going to show you is a scenario where we investigated the addition and removal of peering links. So on the example shown on the slide, we would like to know what will happen to our traffic if we are peering with a new neighbor Z, and see how the traffic will be spread over the network and over the peering links. In the next slide, I'll show 2 different kinds of experiments. One where we have added a full BGP routing tables at different locations in the network in order to simulate the addition of a new peering, and scenarios where we have removed the routes previously learned from an existing peering. And the metric here is the distribution of the traffic over the different upstream, the different links with the upstream providers. So this is a simplified view of Géant. On the top of the figure, you see the 6 peering links that we will consider with their load of outgoing traffic. And we are going to remove PR1 to PR4 and then add new peerings on routers R1, R8, etc. And that's the kind of output we can obtain. So on the x-axis, you have the different scenarios. The first one is the default state. On the y-axis, you see the fraction of traffic that is carried by the 6 upstream peering links. So in the default case, you can see that the traffic load is already highly unevenly distributed. So PR2 here carries 50% of the outgoing traffic. So now in the red scenarios where we remove a peering link, we can see, for example, the del PR2 example. Here in this case, we remove the link with PR2, and we can see that another peering link now carries all the load previously carried by the link with PR2. So it's something difficult to predict by hand. In the case of the addition of peering, we can see in the case of the addition of peering with R1 that the new peering link will take all the traffic that previously went out through PR2. And well, so you can see that for different scenarios. Second experiment we have done is investigate what will happen when internal links will fail and how the traffic will be redistributed, and also how many routing changes each link failure can cause inside my network. Here we have classified each routing change according to what's shown on the slide. So we have looked at routing changes that just change the reachability of destination. So in this class we will see prefixes that were reachable before the link failure and that are not reachable anymore. Peer change are routes that are going out through another AS. Egress change is still through the same AS but through another egress router. And then we have in intradomain routing changes. So this is just a summary here. On the x-axis you have all the link failures, and on the y-axis you have all the routing changes, and the colors indicate the class of the routing change. So what we can observe here is that a single link failure can cause more than 500,000 routing changes. So it's accumulated over all the routers in the network. That's the first observation. And a second observation is that most routing changes are changes at the interdomain level. So these are peer changes and egress changes, not only changing between well, things that wouldn't be seen by traditional capacity planning tools. So as a conclusion, we have a tool that can be useful for you to try to predict the impact of various changes or events inside your network on your BGP routing or your traffic. We have applied it to 3 different networks. We'd like to apply it to other networks. So if you are interested in the tool, do not hesitate to contact us. And we would like to tell you, but I'm sure you know, that many of the changes that are caused in network are interdomain changes. That's why the modeling tools that you use should take into account BGP routing. We have some direction for further work. Try to predict the impact on the inbound traffic, but that we need a better view on the internet topology. We also had the tool support for BGP and PLS VPNs, and one way to compute more accurate failover matrices that were proposed by Thomas Telkamp from Cariden. So that's all. Thank you for your attention.